Welcome to solverfy.
Okay, this is question 28.24, where we have a rectangular loop here with dimensions 4.2 centimeters by 4.2 centimeters by 9.5 centimeters. And there's going to be some current I flowing in this wire, but we don't know the direction yet. But we know that the magnetic field at the center of the loop is 5.5 times 10 to the minus 5 Tesla, and it's pointing out of the page. So, oh no, I'm sorry. It's pointing away from you as you view the plane. So if this is sitting flat in the page, then it's pointing straight into the page away from us. So I'm going to define these quantities here. You'll see why in just a second, where A is actually just half of the length of one of these sides, and B is the length of half of one of these, of the other side. So 2A is 4.2 centimeters, which we can convert to meters like this. And 2B is going to be this long side here, 9.5 centimeters. So we can, if we want, just solve for A and B by just dividing this by 2. So A is going to be 0.021 meters, and B is going to be 0.0475 meters. So I'm using these definitions of half of the length of the y of each side here because I'm going to look at equation, this is from the textbook, equation 28.8, where this integral was done, where if we have some vertical length or horizontal length of wire and we want to find the magnetic field at a certain point, in the book there was a derivation of how to integrate the Biot-Savart law to get the formula for the magnetic field from that segment of wire. So take a look at equation 28.8 if this doesn't seem familiar. And so this equation is defined where we have A is this half length coming up here, and then X is this horizontal length. So in this case, a horizontal length here is B. So I'm going to just rewrite these variables in terms of what we want here. So this would be the magnitude of the magnetic field just coming from this vertical segment on the left here. So let's start adding up. We're going to have 4 total contributions. So we know that there are really going to be 2 of these because we have 2 of these vertical wires, and they're going to contribute a field in the same direction if the current is flowing in a loop through this. So I'm just going to turn this 2 into a 4 because I'm going to multiply this whole expression by 2. So this is going to be the magnetic field coming from these 2 vertical wires. So now the horizontal wires are going to be, this is really going to be the same expression. We can use this expression, except now A and B are flipped. So imagine if we just rotated this entire expression, this entire rectangle. Now our A and B are switched. So instead of A here, we have B, and instead of B here, we have A. Now B squared plus A squared, if we switch A and B, we get the same thing. So this is really not going to do anything different for us. So again, this comes with an extra factor of 2 that I added in because we have 2 horizontal wires. So this is going to be the total magnetic field from, oops, I think I missed a factor of the current because we're going to need the factor of the current in this and all of these. So I'm going to bring back in that factor of the current. I didn't fully reproduce that equation correctly. So we have the current in each of these as well. So now let's just simplify this equation by combining some of these terms and factoring it out. So notice that we have a factor of mu naught over 4 pi, and we have a factor of I, and then we also have this factor of square root of b squared plus a squared in each of these terms. So I'm just going to consolidate that and pull those out front. So we have this term, and then we have this term, and then we have a factor of, we'll be left with 4a over b. Actually, we can pull the factor of 4 out too, because there's a 4 in each of these. So we'll have 4 times I. So we have a over b here, and then we'll be left with b over a over here from this term. So this is what we end up with at the end, simplifying this whole equation. So Now let's think about what we know. So we know what B is. This is a constant, and then we know our B and A. I've solved for these over here. So we want to solve for the current I. So what we're going to want to do is we are going to want to just rearrange this entire equation so that we can solve it for I. So let's start by just pulling some terms over to this side. So we're going to have I, well, let's just do it in a few steps to make it easier. So we're going to have 4 pi times b in the numerator here. That's going to get divided by this mu naught. So that's going to be equal to this whole thing over here. Now notice we have a 4 on both sides, so let's cancel out the factor of 4. We can divide both sides by this square root of b squared over a squared. So let's do that. Put this in parentheses to show that this is all in the denominator. And then finally, we need to divide by this a over b plus b over a term. So that will also go in the denominator here. So this is going to be our final expression for I. So all we have to do is just plug this in and solve it. So let me just make sure that this is all done correctly. So we're going to have I times the magnetic field. So B we can just plug in. We know that. Again, we know the square root of b squared and a squared. We're going to have this factor of mu naught up here. So we'll have, that's 4 times pi times 10 to the minus 7. Okay. And then we have this factor a over b, so 0.021 over 0.0475, and b over a is just going to be the reverse of that, 0.0475 over 0.021. And the result of that whole thing should give us, let's see, it looks like we're getting I is going to be 77.2, sorry, I equals 77.2 amps. So we know the magnitude of the current here, but now let's think about the direction. So we know that the magnetic field is pointing into the page here. So thinking about the right-hand rule, if the current is along the direction of the our thumb, we want our fingers to be curling into the page. So in order to get that, we want our thumb to be pointing clockwise around the outer loop here. So that means that the current is going to be clockwise like this to produce a magnetic field pointing into the page.